This section is about differential equations, which is likely to show up as a free response question. So the first type of differential equations are separable differential equations. These type are the ones that you are able to solve. You want to move the x and the dx to one side of the equation. I put constants over on that side with the x's, and then you move the y and the dy to the other side. I like to keep that side as simple as possible. That's why I put the constants with the x's, and that is so that when I solve for y, it's easier. Then you integrate both sides. You find antiderivatives on both sides. At this point, please make sure you have a plus c on the x side only. You want to keep the y side as simple as possible. And then you solve for y. Make sure your answer is a function. And if you have an initial condition, make sure that your initial condition is on the function and you can solve for c. If you don't have an initial condition, then you can't solve for c. So here's a differential equation, no initial condition, so we will have a c in our final answer. We want to move dx over to the right side. And then we're also going to divide by e to the y. So since e to the y is in the denominator, I'm going to make it e to the negative y, dy, equals 4x squared dx. I left the x on the right side of the, the 4 on the right side of the equation with the x's so that so my y side would be as simple as possible. We can do antiderivatives now. E to the negative y, the antiderivative of that would be negative e to the negative y. Antiderivative of 4x squared would be 4x cubed over 3, and this is when we have the plus c. Make sure you put a plus c in at this point. Your final answer doesn't get a plus c added onto the end. The plus c happens right now. I'm going to divide by negative 1, so I have e to the negative 1 is equal to negative 4/3 x cubed. I still have a plus c. It's a new constant. It's the opposite of the original constant. Now I'm going to take the natural log of both sides. So I have negative y is equal to the natural log of negative 4/3 x cubed plus c. I want the plus c to be part of the natural log. It's not added onto the end. It is the natural log, including the plus c. And the final thing I would do would be divide by negative 1. So I have negative natural log of negative 4/3 x cubed, and the plus c is in the parentheses there. That is how you solve a separable differential equation. There are some specific separable differential equations that it turns out you just need to know, or it's easier if you just know them. Anytime your differential equation is a constant times your function, or the rate of change is directly proportional to y, then that means that you have an exponential function. This is a PERT situation, so then we know y is equal to p times e to the kt. The p is what happened to the plus c. It's actually e to the c, and that is going to be your initial condition. So p is y of 0. And then the other one that you should know is the logistic differential equation. The logistic differential equation has a constant times y, but then also multiplied times the difference between the carrying capacity and y. So your point of inflection is going to be where your growth rate is the fastest. That's going to happen when you get halfway to the carrying capacity. The carrying capacity is a horizontal asymptote. And if it's not set up in this beautiful way, where you can initially see the carrying capacity, you can get it by setting dy dt equal to 0, because the slope would be 0 when y is equal to 0 over here at this asymptote, and also when y is equal to m over here at this asymptote. Those are kind of the things you need to know about logistic differential equations. This line in blue is the solution, And remember how all differential equations can produce a slope field, and that slope field helps us see the shape of that logistic function. Sometimes it's not possible to solve for your differential equation, and in which case we might use an approximation technique called Eulers method. Euler's method is cutting it into tiny short line segments to approximate values of functions. The way this works is we start with our initial condition, so we're starting with f of 1 equals 2. We have delta x, which won't ever change, delta x for us because we're using 2 equal steps, and we're going from 1 to 0, so delta x is going to be negative 1/2. And then we have dy dx, which we can get from our differential equation, and we multiply these two things together to get delta y. So our initial point is 1, 2, since our delta x is negative 1/2, and then we're going to do our dy dx would be 3, because 1 plus 2 is 3. So our delta y would be negative 3/2. That means that our new point, since our x's are going down by 1/2, would be 1/2, 1/2. Delta x is still negative 1/2. dy dx, if we add x plus y together, is 1. So delta y is negative 1/2. We multiply delta x times dy dx. And so then if we take one more step, we'd be at x equals 0, and our y-coordinate would also be 0. So that's Euler's method. Euler's method is a linearization tool. So since it is sort of linearization using short little line segments, the concavity of the graph affects the approximation. So if your graph is concave up, then your approximation would be an underestimate because you'd be using straight little line segments to approximate it. And if your graph is concave down, then that would be an overestimate because you're using short little line segments that would be on top of the curve to estimate it. Those are some really big ideas to have for differential equations. This was an entire chapter, so if you want to review that, that would be an entire chapter to review. Thank you so much. Bye.